So we're starting lesson 512, and this focuses on can two transformations be equivalent to each other? And what that means is if I have a horizontal shift in a function, can I represent that with a different transformation? Or if I have a vertical shift, can I represent that with a different transformation? If I stretch it, how else can I write it besides using a stretch factor? And so that's really what the main idea behind this lesson is stretching exponential functions, can we represent those using a different transformation? So we're going to be using our ideas of A, H, and K in here like we've been doing all year. And so this video focuses primarily on prompt 512. And we're looking at equivalent transformations. And this is really a algebraic beginning to it. And so in this one we're looking at can we do two transformations with the same result? So in other words, if I do a horizontal shift, can it also be a stretch factor? So two different transformations, but they're equal to each other is what that first question is saying. So we're going to use the function k of x equals 5 times the base of 2 raised to the 3 times x minus 2 power. And we're going to try and transform it. And we're going to try and transform it to equal y equals a times b to the x power. What's important about this is going to be the final structure of our answer. So we have to use this as a template. We want a coefficient. We want an a value. We want just one base, b. And one thing to really pay close attention to is we only want x as a power. That is what we want, just x. That doesn't say x minus 2, x minus h, x plus 15. Our power is only x. We need x to be all by itself. So we're looking for a coefficient. So we're looking for a coefficient a. We're looking for a single base, one number for the base, and a power of just x. That's our goal. And we're going to use k of x equals 5 times the base of 2 raised to the 3 times x minus 2 power. And so right away, if I'm thinking about this, I can't have the 3, I can't have the minus 2, I have to find a way to get rid of those. And I'm going to do it in different parts. First, I'm going to realize that cubed power can really be taken in to the 2 right away. I can take that 3 and I could bring it in right away. And I'm going to leave that x minus 2 alone. So in other words, what it's really like I'm doing here is I am taking the brackets and I'm going to put them around there and leave the x minus 2 on the outside. So my parentheses are really going like this. And that way I can look at it as 2 cubed. So that's going to be the first thing that I do. And so I'm just going to write it down, k of x equals 5 times 2 cubed, and that's going to be raised to the x minus 2 power. So that is the first step I did. I brought that in, or I shifted the parentheses around everything except for that x minus 2. And I can now say, hey, 2 cubed is 8. So this is what I have right now. And you may go, okay, well, let's see what we want. Well, we want a coefficient. Okay, well, I got one. I don't know if it's the right one, but I have one. I want a singular base. I have 8, so that's good. But x needs to be all by itself. And right now it says x minus 2. And so this is where we get our algebraic techniques in. Is if I look at this and I go from here and I want to now change this, I need to find a way to rewrite x minus 2 with a base of 8. So I have to go back to my mind and think, what does it mean to subtract exponents? What property tells us that we subtract our exponents? And that is your quotient rule. When you are dividing like bases, you subtract the exponents to combine them into a single base. So what I'm going to do is I'm going to keep the 5. But I'm going to change. And I'm going to say that 8 is going to be separated into a quotient because I'm subtracting my exponents. So one of those is going to be 8 to the x power. and on the bottom is going to be an 8 squared. Because if I think about my properties of exponents right now, I would subtract those to get a single base of 8 to the x minus 2 power. So what I'm really doing is I'm looking at my properties of exponents backwards. And when I say the word backwards, if I'm doing an operation backwards in mathematics, I wonder what we're trying to get into in this section. So I have this right now, and you may go, okay, well, how does that help? Well, right off the bat, I can see something. On the top there, I only have an x. And that's awesome, because that is the hard part. I only want an x, I've got it. And that x is attached to a base. That x is attached to just an 8. I've got it. So what don't I have right now is I don't have my coefficient. You may think it was that 5, but I have that 8 squared on the denominator there. So I have a k of x equals, and I'm going to do 5 over 8 squared, because that can be pulled out as a 1 over 8 squared, so 5 times 1 over 8 squared, and that'll be to the x power, which again can be simplified to 5 over 64, 8 to the x power. So, only x, check. A single base, check. A coefficient, check. There I have it. So is it possible to rewrite an transformation in a different form? Because really, what you have to look at it as, this right here is a horizontal shift. X minus h, x plus h, those are horizontal shifts when it's paired up with the x value. And if I look at it now, I can realize with this horizontal shift here, I can also represent it this way, which that way is a vertical stretch or vertical compression because of this coefficient. There is no more horizontal. So what we really did here is we made a horizontal shift, that x minus 2, into a vertical stretch. And that's what the whole idea is of this lesson, is can we represent two different transformations and have the same result from them? So can I represent them the same even though they're two different transformations? And the key here, you saw me write this down, is, you're subtracting exponents, so we had to divide like bases. So one of the keys, and it's going to be key to this entire section, in this entire chapter, is to remember our properties of exponents. That is a huge thing in this chapter, which is why this is a really good opening question for this lesson. The next video will go on from 513. So for this prompt, 513, we are looking at the graphical representation of two different transformations being equal to each other. In prompt 512, the previous one, we looked at the algebraic way, which was really big focus of properties of exponents, which is going to be a key idea in this chapter. Now in this prompt, we're looking at just graphically. And so you can see right now, I already have highlighted that we want f of x to equal 3 to the x power. And I want to graph both f of x on both axes. And then I'm going to look at a g of x function, which is represented by a horizontal shift, because it's x plus 2. And then I'm going to look at a vertical stretch for h of x, because it's 9 times that function. And I want to see how they relate to each other. So first off, let's graph the parent function for 3 to the x power. And I'm going to need a table for this. And when I'm looking at the table, I'm going to plug in from -2 to +2. And the main reason why is now if I'm thinking about 3 to a power, as soon as I hit 3 cubed, I'm at 27. So I already know it's exponential growth. It's growing fast. 3 to the 4th, 81. I don't want to fit that on this graph. So I'm going to set up my table. And you have to remember what a negative exponent is. A negative exponent means 1 over that positive power. It means it's on the wrong side of the fraction. So if I have 3 to the -2nd power, that's 1 over 3 squared. So 1/9. 3 to the -1st power is 1 over 3 to the 1st. So 1/3. And so I get those, and I can use them to graph my parent functions, f of x. And I can see right away it looks like it's going to approach the horizontal axis, the x-axis. So I have a horizontal asymptote at y equals 0. And now I'm going to go a little bit further. I'm going to graph g of x equals f of x plus 2. And we're going to use green for that one, and we'll use purple for the other one. All right, so we're asked to write an explicit equation and sketch the graph. So let's go ahead and describe the transformation. So if I have g of x equals f of x plus 2, well, I'm going to find f of x plus 2 first. And what that means is x plus 2 is now your input into the function. So rather than inputting x, I'm inputting x plus 2 there. And so I'm going to have 3, and I'm going to use a parentheses because that is an object in the parentheses. And by the way, get used to that. It's going to help you later on in the chapter. So that is f of x plus 2. However, I want to write it as g of x. So, that equals g of x. So g of x equals 3 to the, and I could also write it this way if I wanted to, and that says that 3 is going to be raised to both of those. So either one of those is acceptable for us. Now, what does that mean? That's my g of x. So what's the transformation that I'm looking at? Well, it's x plus 2. It's an h value. So my h here is negative. So I'm going to have a shift 2 units left. What's going to happen is every single coordinate here, every single value in that f of x graph is going to be moved to the left 2 units. So let's go ahead and move it. So you would be able to take your pencil or your marker or your pen and just move every point to the left 2 units. And that works. Now with the nice good old iPad, I could take this, go here, duplicate it, and just slide it over 2 units. And I'm going to change the color to green to represent the function, and I'll erase f of x, and we will name it g of x. And that's the graph. So I have my equation. I know that g of x equals 3 to the power of x plus 2. I have my graph, and I have the transformation. One of the big things I've been noticing is the following directions. Don't just look and think you know what you do. Make sure you're answering every part of the question. Now, h of x is following the same idea. In this case, we're going to have the same process. We're going to first write an explicit equation, then we're going to sketch the graph, and we're going to state the transformation. Well, in this case, we say that we have 9 times f of x. Well, that means I'm going to have 9 times 3 to the x power. F of x equals 3 to the x power. So I'm really saying 9 times 3 to the x. So that actually is my explicit equation. I have h of x equals 9 times 3 to the x power. Now, what does that mean? That, if you have it being multiplied, that's going to stretch the original output. The original output was 3 to the x. I'm taking that original and multiplying it by 9. It's going to stretch it up really, really, really far. So all of these values are going to be multiplied by 9. So this is a vertical stretch by a factor of 9. That means I'm going to multiply by 9. So every single one of those points, you multiplied by 9, which is, by the way, really nice that we have a table there because it's going to make that output multiplication a lot easier. So if I take the 9 times the 1/9, which is a negative 2, I'm going to get 1. If I take the 9 times the 1/3, I'm going to get 3. If I take the 9 times the 1, I'm going to get 9. And so those, again, all I did was multiply those over. I took the original numbers and I multiplied by 9, and that is what gave me the outputs that I just plotted. I'm not going to do 3 times 9 because that's beyond the graph. And I'm going to sketch this, and I'll actually sketch this one rather than copying and dragging over. And I have this, and this is my graph for h of x. So that one was a vertical stretch by a factor of 9. G of x, if we look over there, was a horizontal shift to the left 2 units. What do you notice about these two graphs? So if I'm looking at this, both of them have a y-intercept that is exactly the same. Both y-intercepts are at the coordinate 0, 9. So I know they both have the same y-intercept. And this is exponential, so I want to check the exponential growth. And in this case, they do. They both have the same exponential growth factor here. It is by 3. each one of those, if you multiply by 3, you're going to get the next y value. But look at the green. This y is 3. The next one is 9. This y value is 1. 1 times 3 is 3. 3 times 3 is 9. I have an exponential growth factor of 3 there. If I look over here, it's the same. This is a 1 for a y, a 3 for a y, and a 9 for a y. That also has the same exponential growth factor. So in other words, both graphs are the exact same. But one thing we do need to realize is in order to do that, we have to look at certain characteristics. So I didn't just go, yep, they look the same. I had to check, are they going through the same points? And a really good one to check is the locator point. And for an exponential, it's the y-intercept that's your locator point. It's also, when it's exponential, important to check the growth factor. Just like if you want to check if two linear functions are exactly the same, you're going to check the y-intercept, you're going to check the slope. And that's really what we're doing here, but we're doing it with exponential. The locator, which is the case, is the y-intercept, and instead of the slope, the exponential growth. And so this is prompt 513. We're now looking at prompt 514 on lesson 512, and this one goes back to what I did in prompt 512. I looked at the algebraic technique for verifying if two different transformations yield the same result. And in this case, we're given f of x equals 3 times the base of 4 to the x power, and we're asked to use, and pay attention, read the directions for a problem, read the prompt. It's telling us to use the properties of exponents. That's my hint for this problem. And I want to show these two are equal. And what that means, we get to this the further you go in pre-calculus with identities, is what we call them. But what that means is you want to prove that the left-hand side, LHS for left-hand side, equals the right-hand side. That's what you want to prove. And since it says use properties of exponents, I am going to use and think about my product rule. And the reason why I'm doing my product rule is I can see what I'm going to be going through. I might want to use my quotient rule. We did that in prompt 512. But in this case, I'm going to think about my product rule. I'm going to give that hint as we begin this problem. And so I would write it down. And that product rule goes both directions. And so I'm actually wrote it here backwards, probably the way you're used to. You're used to saying, hey, if you're multiplying two of the same bases together, you can combine them into a single base by adding the exponents. That's probably the way you're used to seeing it. But equal signs go both directions. So I can also say, hey, if I'm adding two exponents together, I can separate them by using the same base and put a multiplication in between them. That's going to be our key for this prompt. So in this case, I know what f of x equals, and I want to show f of x plus 2 equals 16 times f of x. In other words, I want to show a horizontal shift equals a vertical stretch. Let's go back to what we're doing this entire lesson. X plus 2 is a horizontal shift. 16 times f of x is a vertical stretch. I want to prove those two are equal to each other. And so let's start. Well, my input now is x plus 2. So I'm going to input that in for my exponent. So I have 3 times, and I'm going to use parentheses, 4 to the x plus 2 power. And I want that to equal 16 times f of x. Now, when you are dealing with identities, if you're trying to verify left-hand side equals right-hand side, you only work with one side. You don't move things left or right over the equal sign like you're solving. One side stays exactly the same. And so, you know what? I'm going to pretend that this right-hand side is cemented down. Notice I used gray there for cemented down. And I am not going to change that side at all. That is locked in. Nothing's going to change on that side. I want that left side to equal 16 times f of x. Well, what do? Looks like the product rule to me. Look at that, x plus 2. I can separate that, and that's what I'm going to do. I'm going to keep that 3, but I'm going to take this, and I'm going to separate it into 2 of the bases of 4 with a multiplication sign in between. I'm going to say I have 4 to the x power. And I have it being multiplied by 4 squared. Perfect. And so right now, I can see what I'm dealing with here. I can see exactly where I'm going. So let's keep moving it along and see what's going to happen. And if I have this, I'm going to move the 3 and the 4 squared together because they're both numbers, so they both become coefficients. So these are going to combine, and I'm going to have 3 times 4 squared times 4 to the x power, and somehow that equals my right-hand side. I'll put that there both times. And so right now you may be going, well, how does this even beginning to become what I want? Well, I want a 16. I mean, the whole idea is you know what it should equal. I know I have to have a 16. Isn't 4 squared 16? I've got it. I've got the 16. It's taken care of. It's locked in on the right side. Now I have it, and it is locked in on that left side. I wanted a 16. I have the 16. Done. What do I need next? I need the f of x. That's what I need. So what am I left with? I'm left with the times 3, and I still have that 4 to the x power. So that's what I'm left with. So I need to find how can I get that f of x from that 3 times 4 to the x power. Well, look at this. What does f of x equal? Go back to the original. F of x equals 3 times 4 to the x power. That blue is f of x. I have 16, and that blue right here is what f of x equals. So I have 16 times f of x equals 16 times f of x. My left-hand side equals my right-hand side, which you get to write down 3 more letters. And those are the most important letters in mathematics. That is Q, E, D. QED means quod erat demonstratum, which is Latin for thus it has been proven. It makes you sound really intelligent when you say QED. Thus it has been proven. The left-hand side equals the right-hand side. But the main idea behind this is you don't really need to know what QED is. It's fun. We're going to get there, though. Don't worry. The main idea we're going to have to deal with is using your properties of exponents to separate one base into 2 bases. Whether that's using your product rule, like we did in this part A, or in prompt 512, where we used our quotient rule, and we wrote it as division. That's the main idea behind this. And we can even do it here. And in this case, I want to prove the left-hand side equals the right-hand side. And I am going to cement down this right-hand side. Nothing is going to touch that. I'm not going to move anything over. It has been cemented and locked in. I have to change the left-hand side and make it equal that. So, remember, f of x equals 3 times 4 to a power. My new input is x minus 1. So I can rewrite this as 3, and I'm going to use parentheses, 4 to the x minus 1 power. And that's going to equal, and I'm just going to put down RHS for right-hand side. Well, what do I do? I'm subtracting exponents. So I wonder, how do I subtract exponents? What happens when I subtract exponents? And that is my quotient rule. When I have a subtraction for exponents, a minus b for the exponent of x, what that means is I divided x to the a by x to the b. Remember, you're used to it going the other direction. Now we're asking you to split them apart. So I'm going to rewrite this. I'm going to rewrite 4 to the x minus 1 power, and I'm going to change it to 4 to the x power over 4 to the first power. And that's going to still be multiplied by my 3. And that equals the right-hand side. So that's where we're at. Now, do be careful. That minus sign is what your fraction is going to become. It's a positive one down there. Remember, a negative 1 means that it's going to go down to the bottom and the exponent becomes positive. So how does this help us? Well, let's just figure this out. I want f of x. So let's do the same thing I did before. I want this, okay? And I know, and I'll put it in blue, I know f of x equals 3 times 4 to the x power. I want that. That has to be on that left-hand side. Well, good news is I have a 3. Right there. I mean, that 3 is already accounted for. I want a 4 to the x power right here. That 4 to the x power is already accounted for. So you know what I'm going to do? I'm going to just put those off to the side. I'm going to say I have a 3 times 4 to the x power equals, now I'm not done yet because you still see that one part that's not highlighted. It's that 4 to the first power in the denominator. So what does that mean if I have a 4 to the first power in the denominator? What's the numerator? And it's 1. This is really 1/4. If I have a 4 in the denominator, that really means you're multiplying by 1/4 because you're dividing by 4. And so that 4 in the denominator really is like having a 1/4 out there. So really, what do I have? I have a 1/4. That blue is equal to my f of x, and I believe that is exactly what I wanted. I wanted to show f of x minus 1 equals 1/4 f of x. I wanted to show that a horizontal movement to the right 1 unit, x minus 1 is a horizontal shift to the right 1 movement, is the same transformation as a vertical compression of 1/4. That is what that statement part B is telling me, is that a horizontal shift of 1 unit for this function is equal to a vertical compression of 1/4. The main thing, this is going to be huge for this entire section and chapter, is learning to use your properties of exponents differently, the other way than what you're used to. And we'll move on to the last prompt in this lesson. Last prompt for this lesson is prompt 515, which is really a horizontal shift versus a vertical stretch. And that has been what we've been working on in all the previous problems. Is in the last one we showed algebraically that a horizontal shift can be equal to a vertical stretch. Now we're going to look at it graphically. And so what we see right here is this is the parent graph of y equals 2 to the x power. It's increasing exponentially by a growth factor of 2. And we can see that because this has a y-intercept of 0, 1, and we call that, again, for exponential, that is your locator point. And so we have 0, 1. And if I go up to 1, we can see this has 1, 2. And so my y value grew by a factor of 2. I multiplied by 2. When I go to 2, it went up to 4. And if I went to 3, 4 times 3 would be 8. It'd be the coordinate 3, 8, 2 cubed. And that is the parent function for y equals 2 to the x. Now what we're going to do is we're going to just look at pre-done graphs of a horizontal shift and a vertical shift of 2 to the x power. And those are right here. The same curve can be obtained by doing a stretch factor of the original or by doing a horizontal shift to the left. And so notice this. You are stretching the original. You are pulling it up. It's a vertical stretch. Or it is a shift to the left. Not a shift to the right. It's a shift to the left in this case. And it wants you to see here what we're really noticing. And if I have 8 times 2 to the x power, or if I have 2 to the x plus 3 power, they are equal to each other, even though they're two different transformations. And this is what this graph is trying to show you. If you look at it, how can I tell that they are equal? What characteristics am I looking for here? What do I need to know in order to figure out if two graphs are equal to each other? And in this case, what I need to know is I need to look for the y-intercept first, the locator point. Do they have the same y-intercept? And in this case, though you won't see it on the graph, it does. It would be the coordinate 0, 8. As you see, I kind of plotted it above. I could even write it in there, and I encourage you, 0, 8, 0, 8. Yes, they have the same y-intercept. Perfect. The next thing you want to look for is, do they have the same exponential growth or decay factor? And in this case, it's growth, and they do. They're both still being multiplied by 2. They're being stretched by 2 both times. And so I want to look for the growth factor. Again, I said this in one of the previous videos that it's just like slope-intercept form. If you want to prove that two linear equations are equal to each other, you check, do they have the same slope? Do they have the same y-intercept? Because the slope is its rate of change, and it's a constant rate of change. For an exponential, the rate of change is an exponential growth factor. You still check the y-intercept, but you want to look for the exponential growth factor as well. And so we have those characteristics, and that is really what I want you to take away from part A there, is I want you to know what do you look for to determine if two graphs are equal to each other, if they are different transformations. By the way, I could prove it algebraically, and boy, that would be fun just to do that right now, go on a little tangent and take 2 to the x plus 3 and show that it equals that. I'm fighting that temptation. Don't worry, I'm not going to do it. Let's just go to part B. And it says, the graphs do help demonstrate it, but they do not prove it. So there's no proof. Proofs are algebraic. QED, quod erit demonstratum, thus it has been proven. That is proofs. What we're going to do here is we want to show. And if you ever want to do a proof, you have to do it with all symbols. It's going to be fun. If I want to show y equals b to the x plus h power equals y equals a times b to the x. I want to prove that this equals this. I want to prove that b to the x plus h can be equal to a times b to the x power. And really, a is any coefficient. A could be any coefficient that I want. I just need a coefficient, and a is going to represent it. I'm going to use the left-hand side, and I want it to equal the right-hand side. So, what do I do? And by the way, you kind of wish I was doing this with the problem up above now with that 8, don't you? Because these are all letters. Numbers would be so much easier. But I'm not going to go through the entire thing. I really need you just to understand the first process and what you do afterwards, what you're really creating by that first process. And the first process is to determine, are you working with the product rule or the quotient rule? So in other words, are you adding exponents or are you subtracting exponents? That's the first thing you need to do, is you need to look at the exponents and see, am I adding? And if I'm adding exponents, so I'll write this down, if I am adding exponents, I am looking at my product rule. If I am subtracting exponents, I am looking at my quotient rule. That's the first thing I need you to do when you're looking at breaking apart. Is what am I dealing with, product rule or am I dealing with quotient rule? And in this case, I'm adding. So I can separate these. And I can write it as a b to the x power times a b to the h power. That's what I can do. And I understand it's variables. It's a little bit more difficult to do. So let me try something out. Let me go ahead and say, what if I have a 2 to the x plus 3 power? Let's use numbers instead, because variables can represent numbers. So if I can do it with numbers, I can do it with variables. If I can do it with variables, I can do it with numbers. So in this case, same idea. I have the product rule. So I'm going to break this apart. I'm going to use a 2 to the x power, and since I'm adding my exponents, I'm going to look at it as my product rule, and I'm going to use a 2 cubed. And just think, those would combine with addition. What happens to that 2 cubed, by the way? Again, I know we're working with just variables, but let's figure out what happens. Well, that's 8. That's a coefficient. I mean, this right here would be a coefficient. I mean, that would be 8. And then it'd be 2 to the x power. I tricked you. If you look up above, didn't I just prove that those two graphs are equal to each other algebraically? So really what happens is this. This b to the h is going to become a number. It's going to be a value. You're going to have 2 or 3 or 4 or 5 as a base, whatever number is a base, raised to a power that you will know. You'll know what h is. It's going to be plus 2, minus 7, minus 3, plus 4, who knows? But this right here is going to become a coefficient. And then I still have left that b to the x power. And if I think about it, I said right in the beginning, all a is a coefficient. So won't that b to the h power be equal to a? And I showed it. Again, I understand that left side with the variables is a little more complicated. I completely agree. It's something just to be interesting to go through and look at. Your takeaway when you're looking at this and you think about it, so far we focus on the graphical idea that vertical stretches and horizontal shifts can be equal to each other, and we looked at the algebraic. Graphing, there's your takeaway. Look for the y-intercepts and look if they have the same exponential growth or decay factors. Algebraically, here is your takeaway. This is the key, like I've said multiple times for chapter 5 here. You need to look at the exponents and determine which properties of exponents is being used. If you're adding, you're going to break it and separate it into 2 with multiplication with your product rule. If I'm subtracting in the exponents, I'm going to separate it with my quotient rule. That's the takeaway for this one. So this is lesson 512. You can go ahead and start the review preview.